students. In the previous video, we have talked about biodiversity of India, and then we have talked about patterns of biodiversity, and in that we have discussed latitudinal gradients, and we talked about regions of high biodiversity in the tropical regions. Okay, chalo. Today we will talk about the second pattern of biodiversity, that is species area relationship. Okay, second pattern of biodiversity is species area relationship. So what is species area relationship and who explained this species area relationship? Let's learn that. So species area relationship was explained by a German naturalist and geographer, Alexander von Humboldt. Alexander von Humboldt was a German naturalist as well as a geographer who explained species area relationship. Species area relationship was explained by a German naturalist and a geographer, Alexander von Humboldt. And he explained this species area relationship while traveling in South American jungles. He was traveling in South American jungles, and during that time he explained this species area relationship. Okay, so species area relationship was explained by German naturalist and geographer Alexander von Humboldt while traveling in South American jungles. Okay, he was traveling in South American jungles. During that time he explained this species area relationship. Okay, we are learning patterns of biodiversity. In that we have talked about latitudinal gradients, and today we are talking about second pattern of biodiversity, that is species area relationship. And species area relationship was explained by a German naturalist and a geographer, Alexander von Humboldt, while traveling in South American jungles. Okay, so what did he say? He said that within a region, species richness increases with increasing the explored area. In a region, if we increase the explored area, okay, in a region, if we increase the explored area, the species richness increases. But it increases only up to a limit. It increases only up to a limit. Okay, what did the Humboldt say? Humboldt said that within an area, if the explored area is increased, if the explored area is increased, then species richness increases, but it increases only up to a limit. So he said that within a region, species richness increases with increasing the explored area, but only up to a limit. Okay, and if we increase the explored area further, then relation between species richness and area, turns out to be a rectangular hyperbola for many taxons. If we increase the explored area further, then relationship between species richness and area turns out to be a rectangular hyperbola for many taxonomic groups. Okay, so what did the Humboldt say? Humboldt said that if we increase the explored area within an area, if we increase the explored area, then the species richness increases to a certain limit. But after that, if we increase the explored area further, then the relationship between the area and species richness turns out to be a rectangular hyperbola. Okay, like which is shown in this graph. See, here on the x-axis area is taken, and on the y-axis species richness is shown. Okay, on the y-axis we have shown species richness, and on the x-axis we have shown area. So initially if we increase the area, the species richness increases. Look on the black line. Okay, if we increase the explored area, the species richness increases. But if we increase the area further, then the species richness decreases. Species richness decreases and becomes stable. Species richness decreases and it becomes stable, and so the graph becomes rectangular hyperbola. Graph becomes rectangular hyperbola. Okay, so initially if we increase the explode area, then the species richness increases, but after some period of time or after increasing the area further, the species richness graph turns out to be a rectangular hyperbola because species richness decreases and it becomes stable. Okay, so this is the simple graph which was explained by Alexander von Humboldt while traveling in South American jungles, and the equation of this graph is S is equal to C A raised to Z. Okay, S is equal to C A raised to Z. See, a Z है 2 નથી. Okay, this is the equation of this graph, and this graph is rectangular hyperbola. This graph is rectangular and hyperbola. And if we draw this graph using log, then this type of graph is obtained. Okay, if we draw the same graph using log scale, or if we draw the graph on log scale, then this type of graph will be obtained. Okay, and equation of this graph is log S is equal to log C plus Z log A. Equation of this graph is log S is equal to log C plus Z log A. This is the same graph which has been drawn using log scale. Okay, so if this graph is used, if this graph is drawn with the help of log scale, then this type of graph will be obtained, and equation of it is log S is equal to log C plus Z log A. Here S is equal to species richness, A is equal to area, Z is equal to slope of the line, which is also known as regression coefficient. Okay, and S is equal to species richness. S is known as species richness, and C is known as y-intercept. C is known as y-intercept. Ready? So what did the Humboldt say? Humboldt said that within an area, if we increase the explode area, then the species richness increases initially, but after some period of time, if we increase the explode area further, then the species richness will decrease and the graph will become a rectangular hyperbola. Graph will turn into a rectangular hyperbola. Okay, and equation of that graph is S is equal to C A raised to Z, and if we draw the same graph using log scale, then its equation will be log S is equal to log C plus Z log A, where S is equal to species richness, A is equal to area, Z is equal to slope of the line, which is also known as regression coefficient, S is known as species richness, and C is known as y-intercept. And Z remains in the range of 0.1 to 0.2 regardless of taxonomic group. For many taxonomic group or regardless of taxonomic group, mostly Z remains same. Okay, mostly Z remains same regardless of taxonomic group, and it remains in the range of 0.1 to 0.2. Okay, evolutionary biologist biologist observed that. Okay, biologist observed that regardless of taxonomic group, the Z or slope of the line or regression coefficient remains same in the range of 0.1 to 0.2. Whether it is plant of Britain, whether it is birds of California, and whether they are mollusk of New York, the Z remains same for all of them. Okay, whether they are plant of Britain, whether we consider birds of California, whether we consider mollusk of New York, the Z value remains same for most of the taxonomic group. Okay, and one line is not written over here, that I will talk in next. I will discuss that in the next slide. Okay, so what has been explained in this slide, that species area relationship is a pattern of biodiversity which has been explained by Alexander von Humboldt while traveling in South American jungles, and he is a German naturalist and geographer, and he said that if we increase the explode area, then the species richness increases initially, but if we further increase the explode area, then species richness decreases. Okay, and the graph will be converted into rectangular hyperbola. Here equation of the graph is S is equal to CA raised to Z, and if we draw the same graph using log scale, then equation will be log S is equal to log C plus Z log A. And here S means species richness, A means area, Z means slope of the line, which is also known as regression coefficient, F is equal to species richness, C is known as y-intercept. And for most of the taxonomic group, the Z remains in range of 0.1 to 0.2, whether it is whether it is plants of Britain, whether it is birds of California, whether it is mollusk of New York. Okay, so one line is remaining that we will discuss in the next slide. So students, we say that for most of the taxonomic group, the value of Z remains 0.1 to 0.2, whether it is plants of Britain, whether it is birds of California, and whether it is mollusk of New York, the value of Z remains in the range of 0.1 to 0.2. But there we were observing the small area, okay? We were only observing a small area, like we were just observing the New York, we were just observing the Britain, and we were just observing the California, okay? So New York, California and Britain are comparatively small area, okay? But if we try to learn the species area relationship across the continent, okay? If we try to learn the species area relationship across the continent, then the area, explored area becomes very large, okay? If we try to learn the species area relationship across the continent, then the explored area, size of the explored area is very large, okay? So if we analyze the species area relationship among very large area like entire continents, the slope of the line becomes much steeper and its value increases to 0.6 to 0.1, okay? Its value will increase, okay? The slope of the line will become much steeper. The slope of the line will become much steeper, okay? So if we analyze the species area relationship among very large area, if we analyze the species area relationship among very large area, then the value of the slope increases very much. Value of the slope increases very much and it becomes very steeper. The slope becomes very steeper and it becomes much steeper and its value ranges from 0.6 to 1.2. So here the value of the Z is increasing. The value of the Z is increasing when we consider very large area or when we learn the species area relationship across the continent, okay? When we learn the species area relationship across the continent, at that time the Z or slope becomes much steeper and its value increases and it reaches up to 0.6 to 1.2, okay? But if we consider a small area and if we learn the species area relationship in small area like in the California, like in the Britain and like in the New York, then the value of the Z will be 0.1 to 0.2, okay? But if we learn the species area relationship across the continent, then the Z value will increase and Z will become much steeper. Slope will become much steeper, okay? Chalo. And if we talk about frugivores and mammals of the tropical region of different continents, or if we analyze the species area relationship of frugivore and mammals in the tropical forest of the different continent, then the Z value reaches up to 1.50, okay? If we learn the species area relationship for frugivores and mammals in the tropical forest of different continents, okay? If we learn the species area relationship of frugivores and mammals of tropical forest of different continents, then the Z value may reach up to 1.15, okay? So this is about the species area relationship. This is the last line that has been written in the paragraph. This means that if we analyze the species area relationship across the large area, then the slope of the line becomes much steeper and Z value increases. Sometimes it may reach up to 0.6 to 1.2 and it may also reach to 1.5 in case of frugivores and mammals. So this is all about species area relationship, which was explained by Alexander von Humboldt. Okay, I hope you have understood this topic well. Chalo.